Hi everyone, my name is Krishnali Lahani and today I'm going to walk you through my MSc Research Project. This project is about building a smart explainable system that recommends the best crop for a given soil and climate conditions. I will keep everything very simple and clear, and I will also show you a working demo at the end. So first, why does crop recommendation even matters? So the farmers today face a lot of confusion. Weather keeps changing, soil conditions are unpredictable, and even the yield levels are not stable anymore. Traditionally, farmers depend on experience or local advice, but that doesn't always work, specifically with climate change. So the whole idea is, can we use data to support this decision? Something that learns from the soil nutrients, climate, past health, and actually gives you the useful recommendation. That's where machine learning comes in. Now, this is very important. My entire research is based on the future work suggested in my base paper. The base paper is called An Approach for Crop Prediction in Agriculture, Integrating Genetic Algorithm and Machine Learning. The author used the genetic algorithm optimized random forest but only one dataset, the ICAR soil weather datasets from India. They even mention the limitations themselves: no climate data, no yield behavior, and no comparison with stronger models like XGBoost. So, in the future work section, they clearly suggest adding more environmental variables, considering climate change scenarios, and expanding the dataset. That's exactly what I did in this project. I expanded the datasets, added new models, and made the system completely explainable. So when I reviewed the existing work, I noticed something. Most papers only use one dataset. Very few actually combine soil, weather, and yield together, and most of them don't talk about the explainability. Farmers don't just want a prediction, they want to know why the system is suggesting something. Even the best paper highlights these gaps and encourages adding richer data sources. So the main gap was clear: no system that integrates soil weather plus climate plus crop health, and no proper comparison between random forests and XGBoost. That's where my project fits. So, my research question is very straightforward. How can we improve crop recommendation by combining multiple datasets and testing different machine learning models while keeping the system explainable? And from that, I build a clear objective: build a combined dataset, train three models, compare them, use SHAP and LIME for explainability, and evaluate everything with proper metrics like accuracy, microprecision, recall, and append. This structure kept my entire project focused. I used three different datasets. The ICR soil dataset. This is what the base paper used. Irish climate data for open metro. This brings in the real temperature, humidity, and rainfall patterns. Eurostat yield dataset. This helps the model understand how crops behave in the Europe. After cleaning and merging, I ended up with the around 10,500 rows and 14 features, which is really solid dataset for this kind of project. Like any data project, this one requires lots of cleaning. I handled the missing values, removed the duplicators, standardized the crop labels, and aggregated daily climate data into monthly levels. After that, I engineered the features that actually help the model, like things like temperature range, rainfall normalization, humidity normalization, and yield z-score. This engineered feature had a big impact on making the model more stable. This is the full architecture behind the system. We started with three sources, then pre-processing, then feature engineering, then three models are trained, then the explainability model using SHAP and Lime, and finally the output layer that gives you the recommended crop plus the explanation behind it. It's modular, so I can swap datasets, swap models, or even connect this to a real time dashboard. So the three modules I compared were baseline random forest, GA optimized random forest, and XGBoost classifier. The baseline gives the reference point. The GRF is directly inspired from the base paper, that's the whole connection with their future work. And XGBoost is one of the strongest models in the structured tabular data. All three were trained on the same merged dataset with an 80-20 split. Here you can see how the models perform. The baseline RF did really well, around 99.12% accuracy. RA optimized RF performed almost the same and XGBoost kept the highest accuracy, around 99.71%, with the micro FN of around 0.9970. So yes, XGBoost is the best performance statistically. But GARF remains the easier to interpret, so it still has a value in real agricultural setting. I didn't want this system to be a black box. Farmers and planners need transparency. So I use SHAP. This shows the features, which features matter the most globally in the model. The line. This explains the individual predictions. For example, SHAP tells us that the temperature range, rainfall, norm, and yield set score are among the most important features. And line breakdowns the recommendations for the single input, showing how much each feature pushed the decision. This is extremely helpful in the real world use. So okay, now let me show you my favorite part, the working Streamlit app. This app basically brings the entire project to the life. Instead of just running the code in VS Code, I created a proper interface where anyone, even with the zero technical knowledge, can interact with the model. On the left side, you can adjust the soil, nutrients, temperature, humidity, rainfall, basically all the important inputs. You can choose the scenarios or start from the scratch. The once you set everything, you just need to click on recommended best crop and the system instantly gives you the recommended crop, the sharp explanation, and a local explanation for that specific prediction. So it's not just giving you a blind answer, it actually tells you why this crop is suitable under the current climate and soil conditions. This makes model trustworthy, usable, and practical. It also shows the real application of my research, how farmers or planners could use this system in the real life. I have added a video here so you can see exactly how the app works and how fast it responds. So to summarize how my work extends and the base paper usually only used one dataset and one model. I explained the datasets to include soil weather, climate, and yield. I compared three models instead of one, and I added full explainability using Sharp and Line. Basically, I took the future work they suggested and turned it into a full working system. Every project has limitations. Mine has few too. I could validate it with the real farmers yet. The dataset is mostly Indian and European. Climate change scenarios aren't fully modeled, but there's lots of scope. I can add more datasets integrate climate change prediction, test other models like Light GBM, or even deploy it as a full mobile app for farmers. So, in conclusion, I built a multi dataset, multi model crop recommendation system that is accurate and fully explainable. XGBoost performed the best statistically. Our GARF remains very useful because of its interpretability. And overall, I successfully implemented the future work of the base paper, adding more data, more models, and more transparency. This system can genuinely support the data driven decisions in agriculture. Thank you so much for watching. If you have any questions, I will be happy to answer.